Matt Knight is a software engineer and security researcher who thrives on solving meaningful problems. Please welcome Matt Knight.
Hi, GNU Radio Conference. Thanks for tuning into our talk on the radio resilience competition. Let's get things started with some quick introductions.
Hi, I'm Sid. I'm the founder of Radio Resilience, LLC.
Hi, I'm Mark from Agitator, LLC. I am a wireless security researcher, and I really enjoy using software-defined radio to break proprietary protocols. I'm an alumnus of the Bastille Wireless Security Research Team. I'm also an alumnus of both of the DARPA software-defined radio competitions, the Spectrum Challenge and the Spectrum Collaboration Challenge.
My name is Matt Knight, and like Mark, I'm co-founder of Agitator, LLC and alumnus of DARPA's Spectrum Collaboration Challenge. My interest in wireless communication technologies and signal processing tools like GNU Radio led me to the information security domain, which is where I apply most of my attention these days. We're speaking with you today to tell you about an exciting event we're hosting called the Radio Resilience Competition, and to encourage you to compete in it. We'll kick things off by providing some background about the competition, how we became inspired to host it, and the problems we hope to solve in doing so. The Radio Resilience Competition is in part inspired by DARPA's prior software-defined radio grand challenges, so we'll share how our experiences from competing in those are shaping the design of the Radio Resilience Competition. We will then transition into talking about the design of the competition, including its objectives, rules, and a walkthrough of the channel simulation infrastructure we have built for the event. Lastly, we will conclude with a demo showcasing how easy it is to get started. And now to tell you more about the inspiration behind the Radio Resilience Competition, I'll hand it over to Sid. Take it away, Sid.
Thank you for that, Matt. I've been running a software business for the last couple of years, but I also studied applied physics. And I had to go back in my 5th year of studying and go back and do one course that was left of my first year. It was electricity and magnetism. It was the hardest thing to do. And I never imagined myself going back to that. But when I found software-defined radio, I was hooked. It was super interesting and it's super approachable. So as I started getting into it, I found GNU Radio, which was awesome. But I also discovered the DARPA SDR competitions, the Spectrum Challenge and the Spectrum Collaboration Challenge. And that got me thinking. And it got me thinking about the progress in radio. Because I think one of the biggest benefits have been unlicensed spectrum. Now that we have unlicensed spectrum, where you don't need permission to broadcast, there's been so much innovation. I cannot live without Wi-Fi. And it's working because devices are well behaved. But I think we should put the bar higher. On the internet, we don't assume that everyone is well behaved. And I think that as things get bigger and there's more users and more devices, that will be the case for the radio spectrum as well. So we got to make sure that radio works, even if people are intentionally trying to interfere. And when we have protocols that can deal with that, I think it will make radio work better also when there's no interference, because it will just be more reliable, period. And to get there, I think a competition is a great way. A big inspiration is the ImageNet competition. It advanced the state of machine learning and artificial intelligence enormously in a couple of years. Because if you organize a formal competition, the participants can measure how they're doing. They can show that they've really improved the state of art. And that's what we want to do for radio as well. So I'll now hand it off to Mark, who will talk about how we designed the Radio Resilience Competition.
Thanks, Sid. The design of the Radio Resilience Competition was largely influenced by our experiences competing in the 2 DARPA software-defined radio challenges. I had competed solo in the first Spectrum Challenge as Team Wasabi, and then Matt and I joined forces as Team How Make Radio in Spectrum Collaboration Challenge. So conceptually, the first Spectrum Challenge was actually pretty simple. Each team was responsible for controlling 2 USRP N210s and transmitting packets over the air between them. The competition itself was carried out at the Orbit testbed at Rutgers, and in order to facilitate offline development, DARPA gave each of the finalist teams a pair of N210s, so each team could replicate the radio hardware locally, just not the execution environment. For the adversarial matches, two teams went head-to-head in a shared channel and were scored based on the number of packets they delivered. So you would be incentivized to transmit all of your packets as quickly as possible, but do so in such a way that prevents your competitor from transmitting theirs. The cooperative matches, on the other hand, were run with 3 teams in the same channel, but your scoring was an aggregate of the performance of all 3 teams in the match. So this meant that you were incentivized to transmit your packets as fast as you could, but also not interfere with your competitors. So we have these 2 scoring functions where the scoring is strictly based on your interaction with your radio and a competing radio or radios. But as a competitor, you only have access to your own code, your own radio. You have no way to run your competitors' radios locally. And so because of this, there was kind of an opaque and slow iteration cycle because you weren't able to have that tight feedback loop of observing your radio compared to someone else's, making changes, and iterating quickly. And so because of this, I feel that there weren't a lot of technological breakthroughs with the first Spectrum Challenge, but it was very successful, in my opinion, at getting a community built around SDR. I've, since starting this, spent the last 7-8 years of my life really interested in SDR. I've worked now professionally with people from several of the other teams in the first Spectrum Challenge. And I think from that standpoint, DARPA did an excellent job of fostering a lot of interest in this space. And this led to going on to the Spectrum Collaboration Challenge, which Matt will now talk you through.
Thanks, Mark. Following the success of the original Spectrum Challenge, DARPA sought to focus their objectives on collaborative radio performance with the Spectrum Collaboration Challenge. Additionally, DARPA designated this competition as a grand challenge, meaning it had a much larger scope and cash incentives for success. To elaborate on collaborative performance, this meant that competitors were tasked with building high-performance radios that were still good neighbors to their peers. Performance was evaluated by pitting competitors against not only each other, but also against environmental conditions and incumbent radios. Competitors would score points for delivering traffic, but only if doing so did not interfere with the operation of other networks also operating in the shared spectrum. This, in essence, was a competition about cognitive radio, radios that could sense and adapt to the RF environment to improve the performance of all spectrum tenants. Additionally, there was a significant machine learning and artificial intelligence angle to the design of this competition. DARPA wanted to show that radios could make machine timescale decisions about optimal spectrum usage. This as opposed to human timescale spectrum licenses that are currently administered, that last years in most cases. To support this, DARPA commissioned a powerful RF testbed to host the competition. Dubbed the Coliseum, it was a supercomputer driving USRP X310s, running match orchestration software to coordinate loading competitor-provided software in various match configurations. While the competition was successful and enormously fun, there were a few key drawbacks that I'll briefly comment on to illustrate some of the key takeaways that informed the decision of the radio resilience competition. First, the game structure was very complicated. At its core, it was a multi-agent problem, since teams controlled many nodes but also had to coordinate with other nodes that they did not control. However, the competition also had a complicated and somewhat opaque scoring system, which meant that it was difficult to source ground truth data to make real-time decisions off of. Competitors had to rely on self-attested performance metrics provided by other competitor networks. In general, competitors had myriad variables to optimize for. However, at the end of the day, raw radio performance was the biggest factor in determining the team's overall performance in the competition. Additionally, while the Coliseum infrastructure was impressive, it came with some big drawbacks as well. First, while the Coliseum was blazingly fast in matches, with powerful server CPUs and NVIDIA AI processors processing GPUs running competitor code, the surrounding infrastructure was slow. Matches required 12.5 minutes of setup and several minutes of teardown time, plus the time spent on the simulation itself. Teams also had to share this resource, which added to the queue even more. This meant that each test period took in excess of 30 minutes in a best-case scenario. However, in the run-up to the actual tournaments, that could grow to actually span several hours. Second, the Coliseum was hard to develop for. We estimate that 80% of our development work went into plumbing, to support the Coliseum, and other compliance checks, rather than into engineering our algorithms. Lastly, the Coliseum was buggy. Of note, the channel emulator had a critical design flaw that would cause it to saturate, and that needed to be explicitly engineered around. In spite of all this, the Coliseum was an amazing piece of engineering. It lives on as a wireless research testbed under the supervision of Northeastern University, thanks to funding from DARPA and the National Science Foundation. I want to briefly give a shout out to and thank the DARPA Systems Engineering and Technical Support staff, who were amazing throughout every step of the competition, and to all the engineers that helped build the Coliseum. The Spectrum Collaboration Challenge was a huge opportunity for Mark and me. We were lucky to have been able to compete. We learned a ton from it, and we are excited to put some of these key takeaways to work as we embark on running the radio resilience competition. To briefly summarize our lessons learned from the Spectrum Collaboration Challenge, I think the big key takeaway was that the SC2 showed that the PHY is not a solved problem. Because so many teams' performance was bounded based on how performant their overall radio design was, that really illustrated that the PHY was a really key variable that still merits further exploration. Additionally, by having such a multivariate scoring system, it showed that with too many variables, you oftentimes don't wind up solving for any one problem completely. Additionally, while DARPA's infrastructure was enormously empowering to an independent and self-funded team like Mark and mine was, it in many ways was not sufficient to push the envelope forward in this domain. We believe that tight testing loops are critical to ensuring rapid progress, and fully reproducible testing environments are a good way to accelerate competitor progress in this regard by removing bottlenecks on shared centralized infrastructure. Having discussed our analysis of DARPA's prior software-defined radio challenges, we will now switch gears to discuss the overall design of the radio resilience competition. Let's begin with our key objective, to improve the state-of-the-art of resilient radio links. To that end, we designed the competition with these tenets in mind. We want to focus on the physical layer, and to design simple rules that incentivize innovation explicitly to that purpose. Additionally, we assert that radio links must be reliable above all else. Thus, our scoring system requires exactly that links be reliable, with no drop packets or duplicate packets to score well. We wanted to provide the lowest barrier to entry possible in terms of cost, access, and complexity. We want to attract a broad swath of competitors, and we want them to be spending their effort on algorithms that advance the state of the art rather than software to support our bespoke infrastructure. Lastly, we want to enable a tight testing loop for rapid experimentation and iteration. Thus, we designed our competition to run entirely in simulation with no RF hardware required. We realized this with a collection of GNU Radio-based microservices that are orchestrated via Docker Compose. Competitors provide their radio software as a Docker container that emits and receives IQ over zero MQ sockets. And lastly, while the competition itself will run in the cloud, the simulator is fully open source and can be run locally for fast iteration by competitors during development. Rather than boring you with a detailed discussion of the rules, I'll instead provide a brief overview of our scoring methodology and will direct you to our website, radioresilience.com, for all the full details. Here's a high-level description of how matches work. Our traffic marshal container will send one of your two radio containers a series of JSON web tokens over 0MQ. The radio container receiving the 0MQ stream will modulate and send its contents over the virtual air to your other radio container. Upon receiving that radio container will then submit those JWTs back to the marshal container to be scored. Because we wish to emphasize reliability, these JWTs must be submitted sequentially to score. Because we wish radios to operate as a reliable tunnel, dropped or repeated packets are penalized harshly. As long as you submit packets sequentially, your score is equal to the sequence number of the highest submitted packet. Skip one, however, and the scoring stops. As mentioned, the competition is powered by Docker-based microservices orchestrated by Docker Compose. Each microservice that has a signal processing function fulfills said function through either GNU Radio or Liquid DSP. Docker Compose configures the infrastructure's networking such that the competitor containers can only communicate with each other via the RF channel emulator. No opening a socket and passing raw ZMQ data directly, because it will not be routable. Lastly, and I want to emphasize this last point because I think it's really exciting, we are providing a fully working environment in base competitor image. This means that out of the box, you will have a working submission-ready image. We're doing this because we want you to be spending your time on building the algorithms that matter, rather than on supporting our bespoke infrastructure. Now, I'll hand things over to Mark for a walkthrough of the microservice architecture.
Thanks, Matt. So as Matt mentioned, the infrastructure that we built is based on a series of Docker microservices that are orchestrated using Docker Compose. And what this means is, as a competitor, you can clone our repository, run a script, and the entire process of spinning up the match execution containers and environment and running the match is all automated. Each container has an installation of GNU Radio as well as Liquid DSP. And the IQ and packets pass between containers over IP using 0MQ. And so we've leveraged the virtual network isolation capability within Docker and Docker Compose to constrain that such that containers can only talk to other containers that they're supposed to. So the blue radio can't directly listen to what IQ is generated by the red radio can't directly transmit IQ to the blue radio, and so forth. The IQ all has to go through the muxer or channel emulator. And then we provide a fully functional competitor radio and execution environment. So we've included a packet transceiver that you can use and submit immediately to the competition if you want it. So here we have the blue radio container. And the blue radio is the set of radios that each competitor controls. So we have a Docker file for building this container. And again, this is populated with an example competitor implementation that you can customize as you see fit, or just build a new container from scratch. We have paths here for the Docker file, as well as some scripts and example GNU Radio flow graphs. And we have the path for gr-RIRC sim, which is a GNU Radio module that we built for the competition. And this includes the muxer as well as a wrapper on Liquid DSP, so you can use Liquid's packet transceiver from within GNU Radio. And I want to comment that I'm a really big fan of Liquid DSP, and I think it's a great type of library to use for this. The reason is that it supports a wide variety of modulation and error correcting schemes. And so you can easily switch back and forth between different file configurations that might have a non-trivial impact on your performance in the face of interference. The only downside to Liquid DSP is that it is not built as an optimized real-time packet radio engine. So the version of Liquid that we have in the containers, we've applied a number of patches to leverage some of the Volt kernels where feasible to improve performance in the receive chain. Now we have the red container. And this is a container which is generating that intentional or unintentional interference signal. Now in Spectrum Collaboration Challenge, this would be called one of the incumbent radios or incumbent jammers. And in SE2, there was this obligation to characterize the behavior of the incumbent radios and protect them. So the teams competing in SE2 would be able to lose points if they don't successfully protect the incumbent. In RIRC, this is not the case. The incumbent is there to lower your score, but not to do anything else. So you have no obligation to protect the incumbent or otherwise alter your behavior in response to it, except to the extent that you need to change your behavior to improve your packet delivery. Then we have the channel emulator. And right now, this is a relatively simple channel emulator. It takes IQ in from the blue and red flow graphs. It mixes them, adds them together, and then adds in some noise to form a channel. And then that IQ goes back out to both blue radios and the red radio. And then optionally, the host can be listening with the example baudline script to observe the IQ that's going on when you're running the match. And this is useful for debugging purposes. This is the same base image as the other infrastructure controlled nodes and is essentially the same image as the competitor nodes.
The last microservice to discuss is the traffic marshal. The traffic marshal, also referred to as the scoring container, is responsible for generating scoring traffic and calculating your score based on what is received over the air. As discussed, the data type sent is a series of sequential JWTs. The JWTs contain sequence numbers and pseudo-random data, but also a signature to ensure that they can't be forged. As discussed, packets must be delivered back to the traffic marshal exactly as sent. The same data in the same sequence with no duplicates. In essence, your radio must be a reliable tunnel to score well. Well, enough about the infrastructure. Let's talk about how to get started. From the beginning, we have sought to make competing in the radio resilience competition super easy. To get started, you just need to follow these steps. First, head over to our website and get registered. Once you're signed up, clone our simulator infrastructure to get started locally. Now, to walk you through the rest of the steps, I'll hand you over to Mark, who will show you a demo showcasing just how easy it is to get started competing in the radio resilience competition.
Okay, let's see what it looks like in action. So we're going to start here by opening up our flow graph in Vim for the Blue 1 radio and resetting it such that it's using no error correction. So FEC 1 and 2 set to 1 means no error correction. And then modulation set to 2 means we are using QPSK. And we'll go out here and run the run headless.sh script. This is starting the containers, which we previously built. The containers are coming online. The match is starting. We can see already that we have errors printed out here saying expecting 7 received or got N. So this tells us that the scoring server is expecting packet 7, but it got something higher than that. And sequential delivery is required for increasing scoring. So because we dropped a packet early on, we're going to have a pretty bad score of only 6. So now we're going to open that flow graph again and change the FEC 1 value from a 1 to a 4. And this is going to add a 4/7 ham encoding to these packets. And the hope is that we'll have a higher rate of delivery. So we're running the match again. We have the container starting. We have the application code ready on Blue 1 and 2 in red in the muxer, and here the match is starting. Now we can see we've already surpassed the previous score of 7 because we have sequential packets getting delivered due to the ham encoding. Now we can see with that very simple change to the flow graph, we're able to have a marked improvement to our delivery rate. That gives us a score of 135. There we have it.
Now, to comment briefly on the competition itself. Effective immediately, daily matches will be run on our hosted simulator leading up to the competition. As soon as you submit a container image to our repository, you will be registered to compete. Daily scores will be published to the radioresilience.com leaderboard page, which you can find by visiting www.radioresilience.com and clicking the appropriate tab. The competition itself will take place on the weekend of October 3rd. Timeline and format to follow. Thanks for your time today and for your enthusiasm. We hope that this is just the beginning. We're looking forward to a successful competition, and assuming everything goes well, we will host additional competitions and follow-on activities to build on our shared success. Thanks very much, and we look forward to hosting you in the Radio Resilience competition. Visit radioresilience.com to get registered and to get started.